if you are a STEM major, especially if you are taking university physics lab or chemistry lab, I'm about to save you a ton of time and suffering. Let's get right into it. So guys, anytime that you make a measurement in the lab, there's this problem. And that problem is that anytime that you measure something, you're not 100% certain that that measurement is accurate. So we get this thing called uncertainty. So for example, anytime that you use a scale, right, and it gives you that number, there's going to be some uncertainty with it. Anytime that you measure a distance, there's going to be uncertainty with it. And anytime that you measure the time that it takes for an object to go someplace, there's going to be uncertainty, right? You'll have to click the button or use a machine, and those are still going to have uncertainty. So the question here is, okay, if I want to calculate the momentum, and all these things have some uncertainty to it, whenever I use the equation, momentum equals mass times velocity, what is the uncertainty in the momentum? How does this uncertainty propagate, right? And again, here, velocity would just be the change in the distance over the change in time, right? Okay. So again, guys, kind of what I talked about, every measurement has some degree of uncertainty. The problem is that whenever we plug in our variables into the equations to calculate a value, it's not obvious how the uncertainty propagates. So kind of like what I talked about with the momentum, right? We're not sure what it's going to be. Now, guys, whenever you take these courses, especially once you get into university physics or like physical chemistry lab, what's going to happen is they're going to show you all of these formulas for certain cases. Like if you have a variable times a variable, if you have a variable divided by a variable, if you have the natural log of a variable, right? They're going to give you some kind of plug and chug formulas to calculate the uncertainties whenever you plug in the values to these equations, right? Now, guys, what I want to tell you is that it's a pain having to use these formulas, because what if you have like multiplication and then you have the natural log of a multiplication, right? And then let's say, I don't know, all this is taken to like the second power, right? It's going to get really complicated really quickly, and it's not going to be obvious how to use these plug and chug formulas. So what I want to show you today is something that is going to save you an insane amount of time, and that is the general form for calculating the uncertainty in a value. And that is this form right here, okay? So I'll talk about it in a little more detail later, but basically all I'm saying is that if I have a multivariable function and each variable within that function has an uncertainty, you can use this formula, plug in every single uncertainty value, and you will get the exact uncertainty, or at least a very, very good estimate. So a very good estimate, okay? And this form, again, it's only going to work as long as the variables are independent of one another. So basically what that means is like, if I had a function of a and b, and it's like a times b, if a was a function of b, or sorry, let me rewrite it this way. If a was a function of b, we couldn't use this because they're kind of like the same variable. And again, we have to assume that the variables are not correlated with another. And then an example of improper usage would basically just be if you plugged in two variables that were actually functions of one another, this wouldn't work. But again, this typically doesn't come up, so let's go and get into the next one. So I want to give you a conceptual understanding of the formula. The derivation actually takes a little while to get the full thing. Let's just kind of understand conceptually what we need to achieve here. So if I have a function, right, we'll just say it's some generic function a, b, c. And it's a multivariable function, and we have three variables. Now, let's say that it would look something like this. It was a times b times c. And let's say that a had some uncertainty, and the uncertainty in a is just going to be denoted by this little delta a. And let's say b had uncertainty, and then we'll say that c had uncertainty. Now, the problem is that whatever these uncertainty values are, how do they contribute to this function, right? That's our big question. Now, if I use that formula that we saw before, so remember, we'll have the uncertainty in my function. Well, that's just going to be the equivalent of the partial derivative of my function with respect to whatever variable, and then you do this ... for each and every variable that you have. Okay. Now, basically, what we're doing here is what I need to know is how much of an effect does each variable have on the function. So if it's multiplied here, right? If these are all multiplied together, they all have kind of like the same. How do I say this? The same amount of impact in the function, right? If a increases by 1 or a increases by 2, it'll have the same effect on the entire function as if b increased by or is multiplied by 2. So essentially what I'm saying is if I take the partial derivative, that tells me how much the function changes for an incremental change in one variable. So it's kind of a wall of text, but basically if you read this, hopefully it'll explain a little more. But essentially all I'm trying to say is that if I change a variable and I hold all the other variables constant, how does that change affect the function as a whole? If it affected it a lot, then you would expect that its error would also affect the error of the function quite a bit. So that's what that basically tells us, okay? Now, guys, if you wanted a rigorous derivation of the formula, I actually have a link in the description, so it'll basically, kind of systematically prove using calculus and some statistics that this function has to be true. But again, conceptually, it just kind of makes sense. All right, guys, so if you haven't taken calculus 3 yet, or the equivalent of multivariable calculus, let's go ahead and understand what a partial derivative is. So basically, it is a derivative of a multivariable function with respect to one variable while holding the other variables constant, okay? And again, if we have a multivariable function, it's like taking a one-dimensional slice out of it and determining the slope. So if I have something like a times b times c, right, and I have this function here, basically what I want to know is, if I want to know what the partial derivative with respect to a is, then I just say, df of dA, and that's just going to be the derivative of this with respect to a, okay? So you basically just treat b and c like they were constants, and then, compute that value. So let's go ahead and kind of go through how to compute it really quickly here. So kind of what I had before, but if I have this function here, so we'll call it q, but q is a multivariable function of x, y, and z. So these are all going to be variables. Now I want to compute the following derivative. So I have the partial derivative of my function with respect to x. Now if I'm taking it with respect to x, that means that, well, let me go ahead and write it out here. That means that if I'm taking it with respect to x and it's a partial derivative, I need to treat these y and z variables like they're constants. So let's go ahead and show how you do that. All right, so when we end up computing this, well, I know that those values are constants. So I can actually just go ahead and pull out those constants here. So it'll be y times z, multiplied by this partial derivative, and I have x left over. All right, guys, now I'm just going to use the power rule like I would for any other derivative. So the derivative of x with respect to x, what's that going to be? Well, it's just going to be 1, right? If I have x to the 1, and then I use the power rule, I'm going to bring down this 1 here, right? So I have 1, and then again, I'm going to have to subtract off 1. So it's going to be 1, x to the 0, which is going to just be 1, okay? So what that means is that my final answer here, and I'll go ahead and write it down here, it means that my final answer is just y times z, okay? So guys, basically, we could do lots of examples, but it's the same thing. You use the same rules, and you treat all the other variables like constants. Okay. Okay, so here's our first example. Let's say you're performing an experiment in which you want to calculate the momentum of a moving object, okay? So again, we need to know the mass because the formula is going to be momentum equals mass times velocity. And again, guys, velocity is just going to be that change in our position over the change in time, right? Well, on average, right? We'll assume that this is just kind of like an average velocity. Okay, so the object moves a distance of 2 meters in 2 seconds. What are the minimum and maximum possible momentum values? Okay, guys, so if we use our formula here, I'm going to just say that, P, we'll say P is a function, we'll say P is defined as a function of the mass, of the change in position, and the change in time, okay? So that is what P is. So now that I've defined this, and I know that time is not a function of, these are not functions of one another. These variables are independent of one another, okay? They're in different dimensions. So what I can do is I can say, all right, well, the uncertainty in my momentum, sorry, that should be a lowercase p. The uncertainty in my momentum is going to be equal to plus or minus, because remember, it's all underneath the square root. So it's going to be plus or minus the partial derivative of P, of my momentum, with respect to m, multiplied by the uncertainty in m, plus the partial derivative of p with respect to the change in position, times the uncertainty in the change in position. Again, all this is going to be squared. Sorry, I'm kind of running out of room. Hopefully you can still see what I'm doing. And then plus the partial derivative of the momentum with respect to the change in time, multiplied by the uncertainty in our time, okay? So again, guys, the partial derivative is just how much the function changes if I change the variable a little bit. And that gives me like the, how do I say this? This is the weight. I'll call it the weight of error, because whenever I multiply this error by the weight of the error, it tells me how much of the error actually goes straight toward the function, okay? And then you have to add them all up to get that absolute value. Okay, so now that we know this, guys, all I need to do is just a little bit of calculus here. So let's go ahead and See, I'm kind of starting to run out of room. What I'll do is let me go ahead and clear this out. And sorry, guys, just go ahead and just bear with me because this is, guys, it's going to save you so much time. I did not know about this initially, and I really struggled. So let's go ahead and work this out. So let's go ahead and start with the partial derivative of the momentum with respect to the mass. Well, that's just going to be delta x over delta t because, again, we treat these like they're constants, and then the derivative of m with respect to m is just going to be 1. Okay, now let's go ahead and calculate the the partial derivative of the momentum with respect to the change in position. So this is just going to be equal to the mass divided by the change in time. And then, guys, finally, I will do my partial derivative with respect to the change in time. And I'm going to have a value of, so again, we're going to have to use the power rule, so I'm going to get negative mass times delta x over delta t squared, okay? So these are all of our partial derivatives now. So what I want to do here is, let's see, I'll just go ahead and plug it into the formula, okay? So I will go ahead and write it out here. Let's see. So I will have delta x over delta t multiplied by the uncertainty in my mass measurement squared. And then I will add that to, let's see here. My next one is the uncertainty, or the partial derivative with respect to the delta x. It's going to be m divided by delta t multiplied by the uncertainty in delta x. Again, we're going to square this. Then my final term here is just going to be the negative mass times d delta x over delta t. And then, again, guys, sorry, I kind of ran out of space, but this needs to be multiplied by the uncertainty in my delta t measurement, okay? So again, guys, all this would be squared, and you didn't take the square root of all this, okay? Sorry, it got really messy, but guys, this is your answer right here, okay? So if I wanted the maximum and minimum values, I would just take this uncertainty, and I would do my momentum minus the uncertainty. So this would be my minimum, and then I'd take my momentum, and then I would subtract off, or sorry, I would add the uncertainty to get my maximum value, okay? So this is going to be our max min. Okay, so hopefully that makes sense, guys. And again, you would literally just plug in our values, right? So the mass is 2, so I would just plug that in for m, and then the distance is 2, so I plug that in for delta x, and then my uncertainty in the mass is that value. So again, guys, you just plug it in like that. So it should be pretty straightforward. So now for example 2, we're given this function q is defined as x times e to the y to the z. So let's go ahead and simplify that function really quickly. So q is defined as x times e to the y to the z. Now this is actually the same thing as x times e to the y times z. Okay, so there's some exponent rules there. Now the other thing is we want to figure out what the value of q is with uncertainty. Okay, so what I'm going to have to do here is, first of all, let's go ahead and write out what it should look like symbolically. So my uncertainty in q is going to be equal to the partial derivative of q with respect to x times the uncertainty in x plus the partial derivative of q with respect to y times the uncertainty in y, and then plus the partial derivative of q with respect to z. So again, guys, you have to take the partial derivative of every single variable that has uncertainty and, multiply it by its uncertainty in this equation here. Okay. So now, remember, we will have to take the square root of this, and again, it's going to be plus or minus because it's all underneath that square root. So what I'll do is I'll just go ahead and compute these derivatives. So the derivative of q with respect to x, well, that's just going to be e to the y times z. The derivative of q with respect to y, well, now we're going to have to use the chain rule. So I'm going to get x times y times e to the y times z, and then I will do the same thing, but now with respect to z. So I will get, let's see here. Actually, did I do that correctly? Sorry, guys. Actually, sorry. This needs to be z right here, and then I will get x times y, and then e to the y times z. Okay, guys. So now that we have computed all of these derivatives, this answer is super simple. All I have to do is plug in this value here straight into the formulas here. So you'll just go here, plug this in for the partial derivative, and then same thing with this one. You'll plug it into the partial derivative, and then your uncertainty values, so these values right here, you're just going to plug them into their corresponding uncertainty symbols here, right? And then what you do is, now that we have these nice variables, right, you just plug in the value for the variables. You plug this entire thing into this nasty equation, and then you will get your answer. So the final answer for this is just going to be Q plus or minus the uncertainty in Q. And I'm not going to plug it into my calculator because it takes forever, but hopefully that makes sense as to how you're supposed to solve these problems. And yeah, that's really it, guys. If you have any questions, always feel free to comment below, and I'll see you in that next video.